All right, so looking at, one of the stresses we just finished talking about was concentration. So now we're looking at what happens if there is a change to volume and pressure. Okay, so I will make note, first of all, that volume and pressure only truly have an impact on gaseous reactants and products, okay? So when you're looking at change in volume and pressure and everything is aqueous, it doesn't really have an impact. It has an impact on if you have something that is gaseous within your equilibrium. So before we can kind of get into this, let's recap the relationship between pressure and volume. So pressure essentially is the number of collisions happening within a container, right? So the more collisions you have, the higher the pressure is, right? So let's say you have a large space versus a small space with the same number of particles, 1, 2, 3, 4, 5, right? And the particles are bouncing around in here, doing their thing, right? Same number of particles. So imagine this is happening, same temperature, same conditions. It's just that the volume is different of where the gas is located. So the container that is smaller will have a higher number of collisions, right? Just automatically, there's less space to work with, so they're just going to be bouncing around within the walls more. Whereas over here, you have a lower number of collisions. A lower number of collisions. So meaning there is less chance of them hitting the wall, or I should say it takes longer for them to hit the wall just because there's simply more space. So you're going to have a lower number. So going along with that relationship, this one would have a lower pressure, whereas over here you would have a higher pressure because it's directly correlated with the number of collisions. So comparing the volume size, if the volume of the container is bigger, the pressure is lower. If the volume is smaller, the pressure is higher. So in other words, pressure and volume have an inverse relationship with one another. Okay, so that's important to keep in mind when we start looking at equilibrium. So here we have a reaction. So we have a blue and yellow making a green. So our reactants are blue and yellow and our products are a green. So this first container here is the equilibrium without the stressor added yet. So what we're going to be doing here in terms of the stress is we're going to be increasing the volume and then decreasing the volume. Okay, so what I want you to understand is that when we're talking about the space that the reaction has, especially with gases, gases will fill whatever space you allow them to have. Right? So if we were to increase the volume, it's going to want to fill the space that you've now allowed it, right? So there's more space there, it wants to fill the space. If you give a gas less space, it will occupy less space. So basically they will condense, there'll be less space between particles. Now how does that work for equilibrium? You have to basically compare the number, or I should say the amount of moles of gas on the reactant side in comparison to the product side. So before we get into that, let's say we had, okay, so let's say we had an equilibrium like this, and you're asked to compare the moles of gas. So when you're not dealing with quantitative numbers, so it's not like they're giving us a mass value. It's kind of like you're just going by the reaction. The only mole values that you have to compare with are the coefficients. So technically on the reactant side here, I have 2 moles worth of gas. And the product side, I have 3 moles worth of gas. Remember, this AQ does not consider because it's not a gas. So when you give, let's say we had this in equilibrium and we were all of a sudden going to give more space, so an increase in volume. The equilibrium will shift to whichever side of the reaction will actually be able to occupy the space better. So if we have an increase in volume, meaning we want to fill a larger amount of space, in this particular reaction, it would shift to the right because the product side has more gas in comparison to the reactant side. And vice versa. Let's say we were to take this equilibrium and shrink it down in the available space that it has. The reactant side occupies a smaller amount of space in comparison to the products. So like I said, the equilibrium will adjust to fit the space that it is in as best as possible. So what ends up happening is if you're decreasing the volume, it would in this case shift to the left because it wants to occupy a smaller amount of space. Now the wording of this can be different. Instead of saying increasing volume, what could be said is there's a decrease in pressure, which means exactly the same thing because remember pressure and volume are inversely related. So the question may say, well, what happens to this equilibrium once there's a decrease in pressure? Okay, well, you have to think, well, that means there's an increase in volume, right? Same thing with if we say decrease in volume. In other words, that's like saying we have an increase in pressure. So let's go back to this diagram here. So here we have our equilibrium without stress, and we're going to lower the volume, which means there is a higher pressure. The reactant side has 2 moles worth of gas, because this is like a coefficient of 1 and 1, right? It's like A plus B making C, and everything's a gas, right? Whereas the product side occupies only 1 mole worth, right? There's double the amount of gas on the reactant side in comparison to the product side. So if you were to count out what's happening here, the smaller amount of space has more product than it did here. So let's look at the green. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this shifted to the right and made more product. Why? Because the product side occupies a lower amount of space. Whereas the opposite is true over here. We're lowering the pressure, which means we're increasing the volume. And what's going to happen here is it should shift to the left side because the left side has more gas particles that could be filling that space. So here we had 9 product. Here we have 1, 2, 3, 4, 5, 6, 7, 8 products. So meaning some of that product shifted to make more reactant. So this shifted to the left. So when you're looking at changes to volume and pressure, you're comparing the total number of moles of gas on the reactant side to the total number of moles of gas on the product side. So reactants and products, you're comparing the mole values. If it's a smaller amount of space, it shifts to the side of the reaction that has a smaller amount of space. If it's an increase in space, it's going to shift to whichever side has an increase in space. So here we have a reaction. So we have nitrogen and hydrogen making an ammonia again. So here we have total gas on the reactant side being 4, so 1 plus 3 moles. Here we have 2, right? Because we only have 1 product, and everything's a gas, so that's why everything is being included here. So let's say we were to increase the pressure, which means the volume is going down. In this case, it would shift to the right because the gas particles on the product side take up half as much space. If this were the opposite, if it was an increase in volume, this would have shifted to the left because this takes up double the amount of space that the products do. Now, keep in mind, there will always be a new equilibrium established once that shift has occurred. It takes a little bit of time, but it will eventually get there. Okay, so one point to keep in mind, okay, and it's not really mentioned a whole lot when we're looking at pressure volume changes, but anytime you decrease the volume, what you're doing is you're automatically bringing particles closer together. So what ends up happening is even though the pressure goes up because the number of collisions with the container walls goes up, the number of collisions happening within the particles themselves also goes up. So you will naturally see the rate of reaction go up a little bit for both forward and reverse. But it's important to keep in mind when you're talking about stress and shifts, you're looking at the main stress and the main shift that's happening. So like, for example, the forward and reverse reactions could both increase if I'm decreasing the volume. But if I'm decreasing the volume, the shift to the left will be more predominant than the increase in rate of the forward reaction. Hopefully that kind of makes sense. So if I'm asking you for a shift, you can't tell me, well, they're both going to go up. You have to tell me which one is the predominant change that is occurring for that equilibrium. Okay, temperature change. So here's our next big stressor. So we looked at temperature change actually when we talked about the K, the impact that it has on K calculations of how it can increase the products or decrease the products depending on what's happening here. I want you to think of, before we get to this, we'll look at this in a simpler way. Okay, so I want you to think of energy when we're looking at, especially looking at Le Chatelier and like shifts and chemical changes. I want you to think of it as either being a product or a reactant here, okay? So meaning, let's say I have an exothermic reaction. Energy is technically a byproduct of this reaction, right? So I have A and B making C and energy. So if you were to increase energy, if I were to increase the temperature here, the equilibrium, like we said, with anything else, it wants to alleviate this stress. So if you add in energy, it's the same thing as saying as if you were to add in excess product. What would happen here is the reaction would shift to the left to try and use up that extra energy by creating more A and B. Okay? If you were to take this reaction and we were to cool it down, right? We were to take this system and cool it down. Essentially what you're doing is you are removing energy. It's like there's a decrease. It's the same thing as saying there's a decrease in the product. So what would happen is this reaction would have to push forward. The rate of reaction for the forward reaction would increase to try and replenish the energy that has been lost. It's almost like as if the same process was happening if we said we were to decrease the concentration of C. The forward reaction would speed up to try and replenish C. The same thing happens here. If you cool this down, you are removing energy. It would push forward in the forward rate of reaction to produce the energy that has been taken away. Okay? If you had an endothermic reaction, right? This is like we have energy being a reactant. So if you were to decrease a reactant quantity, the reaction will shift to the left to try and replenish that. The opposite is true if you were to add it in, right? So if we had all of a sudden an increase in energy, it's like the same thing as saying we have an increase in reactants. It would shift forward to try and alleviate some of that excess reactant or excess energy in this particular case. So when you're looking at this, it's discussing endothermic and exothermic reactions, but I find it easier if students think about it as being a product or a reactant, because if you understand the concentration changes that exist, it's the same thing that is applied here when there's an energy change that exists.